All right, we are in Unit 2. We are in Chapter 9 going over some practice problems, currently in Chapter 9 with some of the homework questions and things like that to make sure we can get a good background. And what we've been looking at is high leverage points. Are they influential points? Do they have residuals or not? How does it affect the line? Would it make the regression line stronger, weaker? So there's not a ton of math other than understanding in this section, I guess, which is why they're basically referring to it as wisdom. But again, if I'm moving too fast for you, pause the videos. After you pause the videos, write down the problems, but I do got to move reasonably fast through these so we can get through as much as possible so they aren't too long. But anyway, a college admissions officer defending the colleges uses SAT scores in the admission process. Produce the graph below. It shows the mean GPAs for last year's freshmen grouped by SAT scores. How strong is the evidence that SAT score is a good predictor of GPA? And what concerns do you have about the graph, the statistical methodology, and the conclusions? So it says SAT scores versus freshman GPA. And it looks like the combined SAT scores are going up as the GPA of a freshman is going up. So currently, if I was to just scan this and try to do a linear regression model, it does look like the trend is going up. I'd have to look at the residuals just to kind of see where that would be, right? See if I notice any kind of pattern with them. But the point is, perhaps the best way to start is to discuss the type of graph that would have been useful for this. The admissions officer should have made a scatter plot with a coordinate for each freshman, matching each individual stat score with his or her respective GPA. All right, instead of just this overall, because for all we know, are you just saying the average? Am I looking at the overall, like, because it says it shows that it's the mean GPAs, right, for the last groups. It shows the mean GPAs for last year's freshmen grouped by SAT scores. So because I'm looking at the freshmen and I'm looking at a mean of all of them, so roughly everybody who scored this, we already said that means of stuff make the line, that regression line, and everything be less off, makes things more concise, more accurate in a way. So if the cloud of points was straight enough, the officer could have attempted to fit a linear model and assessed its appropriateness and strength. So the point is they could be off because they started to use averages, is what we're implying, right? As is the graph of combined SAT scores versus freshman GPA indicates very generally that the higher the SAT achievement is associated with higher mean freshmen, but that's about it. So we can't say that it is a trend other than if it's their average of all of their freshman GPAs. But ideally, you should have taken each individual freshman GPA and their score and plot those points to see where we are at, to see if you see a true association between them. The first concern, though, is the SAT scores. They have been grouped into categories. We cannot perform any type of regression analysis because these variables are not quantitative. All right, we don't even know how many students are in each category. I don't know how many students did any of this. I'm just looking at the data, but we don't know how many students took each part. There may be one student with an SAT score of 1,500 and 300 students with 1,200. We don't know like how many kids scored what, which is again why it would be better individually. So on this graph, these possibilities aren't given equal weight because we don't know. They're making it look that way. So the graph itself is a little funny, I guess is the point of why they would kind of choose to do it this way. And then even if the SAT scores were at all useful to us, the GPAs given are averaged, which would make the association appear stronger anyway, like we said earlier. So finally, a connected line graph isn't even useful at all. For this, it doesn't simplify the situation at all and may in fact give the false impression that we could interpolate between the data points. So all of this graph is just nonsense, basically. Averaging everything together, you're combining the SATs together. I don't know how they could have done on one part and how they could have done on another. Their GPA could have been brought down more because they are not really good at math, and they didn't do very good at math with their SAT score either, but they did very, very well on English and did very, very well here. I mean, we don't know because everything is averaged together here, including their scores. So we don't know. And how many scores did somebody get in certain categories, like they said earlier. So in general, it could have been done in a better, more efficient way. In this one, it says, after keeping track of his heating expenses for several winters, a homeowner believes he can estimate the monthly cost from the average daily Fahrenheit temperature by using the model. Cost equals 130 minus 2.13 times the temp. And here is his residual plot. So his residual plot, I'm not completely noticing a pattern. I mean, maybe there could be something slightly, but they do kind of appear to be all over the place. It says, interpret the slope of the line in this context. It says, as one temperature goes up, like as your temperature goes up is what it appears to be. The model predicts a decrease in $2.13 for the temperature, each temperature that goes up in Fahrenheit, I guess, right? The model predicts a decrease in that, in heating costs for an addition in temperature. So the warmer it gets, the lower its cost, which makes sense. It says, interpret the y-intercept of the line. If the temp is 0 degrees, right? 0 degrees, it would cost him $133. During the months when the temperature stays around freezing, would you expect cost predictions based? What would you expect? So when temperature is around 32, which is freezing, the predictions are generally too high. The residuals are negative, indicating that the actual value are lower than the predicted. So it says during the months when the temperature stays around freezing, all right, so it's around freezing, it says, would you expect costs based on this model to be accurate? So it appears as though what our prediction line is, the residual is negative. That's what's indicating that the values are lower than what we predicted. Okay. So, would you expect cost predictions? I would expect I could plug it in, but I'm expecting that it actually be lower than what I come up with if I'm looking at my residuals. So I'm overestimating with it. In part D, what heating cost does the model predict for a month that averages 10? So they plug in 10, you can get that prediction. During one of the months on which the model was based, the temperature did average 10. What were the actual heating costs for that month? So we'd have to look at it. According to the model, the heating cost in a month with average daily temperature of 10 degrees Fahrenheit is expected to be that. That's what we know. E, during one of the months on which the model was based, the temperature did average that. What were the actual heating costs? Well, the residual for 10 degrees appears to be down here, right, at -6. So remember, it's residual equals observed minus predicted. So it's residual, which is looks like that's -6, equals observed, I don't know, minus prediction, which is that. So if I add that over, whatever's left over would be the observed. So it's that -6, which was $105. And then it says, should the homeowner use this model? It says the model's not appropriate. The residual plot shows what appears to be kind of like a curve. Like I said, it looks like it's kind of curved. And the association between monthly heating costs and average daily temperature doesn't appear to be completely linear either. And would this model be more successful if the temperatures were expressed in Celsius? Again, just by changing what form, it's not going to change all the residuals. The units don't matter. The relationship, association between them is quantitative. Remember, we discussed when you're changing means and standard deviations and things like that, it's not going to change here either. By you altering what the point looks like, it's still all going to be the same. You're just changing the units, and the value of those numbers is still the same perspective, just different units. Taking a look at this, the graph shows the ages of both men and women at first marriage, right? The year, age at first marriage, right? Clearly the pattern for men is similar to the pattern for women, but are the two lines getting closer together? So are those lines getting closer, meaning is the age getting closer? And here's a time plot showing the difference in average age, men minus women at first marriage, and the regression analysis and the association. So that's of men minus women, right? Men minus women. It looks like it is decreasing, right? That's what it looks like. And the residuals, I'm not noticing too much of a pattern here. And when I look at the data with this, all right, it's looking like it's giving me a linear model. I'm not noticing too much of a pattern. It looks like it's negative, so it looks like I could kind of go with that. It says, as we're looking at all of this, what is the correlation between age difference and that? Well, that's your R. So the R would be me square rooting what they gave me. So there it is, but because it's going down, it's negative. The negative value is used since the scatter plot shows the association between negative and strong. The linear model that predicts age from this would be what they gave me, right? That was our constant minus that. And this model predicts that each passing year is associated with a decrease of approximately 0.017 years in the difference between male and female ages. The more meaningful comparison might be to say that it's predicted to be about 0.17 years in the age difference for every 10 years that went by. Right? If we look at this, it says predict the average age in 2015. So you plug in the year, and when we plug in the year, I get about 1.6 is the age difference. So according to the model, the age difference between men and women at first marriage is expected to be approximately 1.68 years. This figure is very sensitive to the number of decimals, though. And then describe reasons why you might not place much faith in that prediction, because it's way outside our range, right? The last data was in 2003-ish, maybe, just around 2000. So that's way out there, so it might be risky for us to assume that. So, all right, when we come back, we will take a look at this.